Hello everyone. In today's lesson we're going to talk about metallic bonding. And the first thing we need to understand about metals is that in metal atoms the outer electrons are weakly held, and as a result they're what we refer to as delocalized electrons. So let's talk a little bit about this word, delocalized. Because of the weak attraction between the nucleus of the metal atom and the outer electrons, the outer electrons are not bound to any particular atom or any particular nucleus, let's say. So delocalized electrons, not bound or localized to any particular nucleus. So these delocalized electrons are able to move throughout this lattice of metal ions. So if we're looking at the diagram down here, we see the positively charged metal ions arranged into a lattice, and then these smaller particles are the electrons. And if we look at any one electron, so if we look at this electron right here, it's not bound to any of these metal ions. It has the ability to move throughout this lattice of metal flow of these outer electrons, or these delocalized electrons in metals. And the attraction that occurs between these delocalized electrons and the metal ions in the lattice is what we refer to as metallic bonding. So there's an electrostatic attraction, as we've been discussing in class for ionic bonding, an electrostatic attraction between the negatively charged delocalized electrons and the positively charged metal ions in the lattice. And these attractions are referred to as metallic bonding. So another name that is frequently given to this model for metallic bonding is the electron C model. And this is because these outer electrons, these delocalized electrons, are free to flow through the network, through the lattice of the metal ions. And that's where this name electron C comes from. So we'll see this phrase used to describe this bonding model, the electron C model, whereby the electrons, again, delocalized outer electrons, can move freely through the lattice of metal ions. And this type of interaction between the delocalized electrons and the metal ions in the lattice leads to a lot of properties, characteristic properties of metals that we're going to discuss here next in our lesson. So when we look at common properties of metals, first of all, metals have moderately high melting points, moderately high boiling points. So not quite as high as some of the ionic compounds that we would have looked at earlier in Chapter 7, but higher than covalent compounds, like water, or ammonia, or things like that have low melting and boiling points. A little bit more important in terms of the electron C model, the delocalized electron model for metals, is the idea of conductivity. So metals, we see, are good conductors of both heat and electricity, and this is actually a result of that electron C metallic bonding model because of the delocalized electrons. So remember, we have these delocalized outer electrons that are not bound to any particular metal nucleus. And as a result, they can move freely through the structure, through the lattice of those metal ions. And those mobile electrons make metals good conductors of both heat and electricity. Obviously, there will be different degrees of conductivity for different metals. Some are better conductors than others. But as a general statement, we do say that metals are conductors of heat and electricity because of the delocalized electrons. And similarly, metals tend to be malleable and ductile. These are terms that we've talked about before. Remember that malleable or malleability describes the property of a substance to be hammered into sheets. So what we're looking at here is compressive stress being applied to a substance. So when you hammer on a metal and apply a compressive stress to that metal, the metal has the ability to change shape in response to that stress instead of breaking apart. And that is what we describe as malleability. This is, again, a result of that delocalized electron C model. Because the electrons are delocalized, it is possible for those metal atoms to sort of roll around each other when compressive stress is applied to the metal. So we do see that the metal can be flattened, hammered into sheets as opposed to breaking apart like you would see with an ionic compound. Ductility, on the other hand, here we're looking at tensile stress. So you think about pulling on something, stretching it out. We talk about tensile stress. Tensile is in tension, right? So when a tensile stress is applied to a metal, we see that it is able to change shape and be drawn into sort of a long wire as a result of the tensile stress. And again, this is because the metal ions in the lattice are able to roll over each other because the electrons in the outer shell are delocalized. These delocalized electrons, which can flow freely through the structure, through the lattice of the metal ions, that allows for those metal ions to sort of roll over each other when tensile stress is applied, and the metal can change shape as a result. So these are some characteristic properties of metals, and we see how conductivity then, as well as malleability and ductility, are related to the delocalized electron C model. Just one other thing to sort of think about here before we go on and talk about alloys when we're looking at properties of metal. We do see as a general statement that as the number of delocalized electrons in a metal increases, so does the strength of the metal. So we should probably write that down here. In general. Always exceptions, but in general, as the number of delocalized electrons increases. We see an increase in metal strength. So just something to think about there. You have more delocalized electrons, greater charge magnitude, greater attractive forces between the delocalized electrons and the metal ions in the lattice. So one other thing we should talk about in our discussion of metals is formation of what we call alloys. And alloys are actually mixtures. So just like a saltwater solution or a garden salad or bag of trail mix, an alloy is a mixture. It's not a chemical compound. So alloys are not formed via chemical means, but via physical means. What it is a mixture of elements that has metallic properties and generally made of metals with some exceptions. So alloys come in two different varieties based on the way that they are manufactured. The first is what we refer to as a substitutional alloy. So we're looking at an image here that shows us a substitutional alloy. In a substitutional alloy, we see that metal atoms in the lattice are actually replaced by other elements with similar atomic size. So in this diagram, we see on the left our pure metal lattice. And then over here on the right, we see an example of a substitutional alloy where some of those atoms in the lattice have been replaced by other atoms of a different element, but of similar size to the original atoms. And so then the substitutional alloy will have properties that are similar to that of other metals, but different than the pure metal. So maybe it has, greater strength than the pure metal, or it has more resistance to, some sort of corrosion or oxidation or something like that. So some sort of beneficial property of the mixture that we don't see for the pure metal. And you're going to be familiar with some of these substitutional alloys. So for instance, an example of a substitutional alloy would be sterling silver, which is made out of silver and copper. Brass and bronze, other examples of substitutional alloys. So let's write a couple of these down here. Let's see. Brass. We all know about brass, of course, if you are in band. Brass is an alloy which is a mixture of copper and zinc. A similar alloy would be bronze, which is actually a mixture of copper and tin. And these are both examples of substitutional alloys. So we're replacing some of the original metal atoms with new atoms of a different element, but with similar size. So then the other type of alloy, different manufacturing process, what we call an interstitial alloy. In an interstitial alloy, we see that the small holes in the lattice of the metallic crystal can be filled with atoms of a different element of smaller atomic size. We call these small holes interstices. So in our diagram over here on the left side of our screen, we again see our pure metal, and then there would be these interstices, small holes in the lattice. And in our interstitial alloy, then, those interstices, those small holes, have been filled with atoms of a different element of smaller size. And so a good example of an interstitial alloy that you would be familiar with would be steel, which is going to be made up of iron, and then another element, a lot of times carbon, of smaller atomic size, which goes into these small holes in the metal. And with steel, it actually increases the strength versus the pure iron. So again, we're getting some sort of beneficial property as a result of the alloy mixture. Okay, so that's our short lesson on metallic bonding. If you have any questions, of course, as always, you can email me or stop by before or after school.